So I have good news and bad news. The bad news is for the people over here. You're going to have to move slightly. The good news is for the people over here. I'll not neglect you. And then there's also bad news for the guy behind the camera because he now needs to move the camera shot a little bit. Very quickly, can I have a brief show of hands? Who in here has had no or very limited exposure to OpenStack up to this point? Can you please raise your hands? Okay, so there's a few, fine. I'm just checking because I have one brief part of my presentation talks about sort of the basics of OpenStack and I don't want to bore you. So if we have a few people who have had very limited exposure to OpenStack, that's good. Okay, so I'll give you about 10 more seconds to snap that QR code if you wish. And I'm going to start talking about high availability and disaster recovery in OpenStack, where we started and where we are now. Are we having a noise issue here? Is this better? Can you still hear me? Okay, good. All right, fine. So HA and DR in OpenStack. First off, what is OpenStack? By the way, this is the brand new OpenStack logo that was just unveiled at the OpenStack Summit in Barcelona the other week. The old logo looked slightly different, had a bit of a 3D feel, and apparently one of the most important things that the OpenStack Foundation needs to do right now is redesign their logo, having solved all other problems, which is a great thing. So let's all enjoy this new logo. Wonderful. What is OpenStack? OpenStack is an open source cloud platform, more precisely an infrastructure as a service platform that is built to drive both private and public clouds. It is not the only private cloud platform, it is also not the only open source private and public cloud platform. It's one of four. The other ones that some of you may be familiar with are Eucalyptus. That's a GPL3 drop-in replacement for Amazon AWS APIs. There is OpenNebula, which is a private cloud solution that is relatively popular, particularly in academic circles. And there's also Apache CloudStack, which was originally launched by Citrix and is now continuing under the auspices of the Apache Software Foundation, which still has reasonable traction, reasonable popularity with commercial hosting providers. And then, of course, there's OpenStack. OpenStack is an open source platform that is licensed under the Apache software license, the ASL 2.0. And the ASL is a permissive license, a permissive open source license. That means you can do pretty much anything that you like with the software, as long as you include the required notices. So for example, you can't remove a copyright notice that's in the code, you can't remove attribution and so on. But other than that, it is a very permissive license. In particular, it's not a viral license and it's not a copyleft license like the GPL, the AGPL, the LGPL, and so forth. This is a fairly significant choice of license because other than or in contrast to, for example, Eucalyptus, which preceded OpenStack by a fairly significant amount of time, OpenStack has managed to make inroads into industries which historically have been relatively averse to open source software, in particular the telecommunications industry. And I think it's really no accident that this is one of the use cases, telco workloads, where OpenStack really shines to this day, and I think it is in no small part due to this choice of open source license. OpenStack originated really at the intersection of science and business. OpenStack was originally a collaboration between NASA, more specifically NASA Ames, which is the research facility that NASA maintains in Silicon Valley. I know we have a few people here that are from either San Jose or Santa Clara or some other places in the area. If you've ever driven down US 101, from San Francisco to San Jose or Santa Clara, that's the big hangar on your left. That's where NASA Ames is based. And so that was one half of the OpenStack collaboration originally, and the other one was Rackspace, which is a publicly listed hosting services provider from San Antonio, Texas. What is that? Well, yes, yeah, they exactly. They recently were in an interesting sort of acquisition, taking the company private and so on. Yes, so you're right. But they were, at the time, definitely a publicly listed hosting provider. So this was in 2010. So 6 years, a little over 6 years ago, this collaboration between NASA and Rackspace originally started. July 2010 is sort of officially the birth month of OpenStack. November 2010 was when we had the first OpenStack release. And OpenStack is now in its 15th release cycle. Releases drop twice a year, and they are alphabetically named. And so after the Austin release, which was the original release, we had Bexar, Cactus, Diablo, Essex, Folsom, Grizzly, and Havana, Icehouse, Juno, Kilo, Liberty, and Mitaka. So that's four. What is that? So Austin, Bexar, Cactus, Diablo, Essex, Folsom, Grizzly, Havana, Icehouse, Juno, Kilo, Liberty, Mitaka. One more time. So that was 14, and we're now in the current release is OpenStack Newton. That's the 14th release, and we're currently in the 15th release cycle. The next release is going to be named Okada, and it's going to drop in April of next year. So we always have release drops in April and in October. If you're interested in how sort of the release cycle works and how OpenStack actually guarantees that it has these very, very timely releases, please feel free to grab me after, and I'll be happy to go over that. From the original humble beginnings of a cooperation between like one scientific U.S. government agency and a business, a hosting provider, so basically two companies or two organizations, one of them being a company, OpenStack has grown to more than 300 OpenStack Foundation members, OpenStack Foundation corporate sponsors, and supporting companies. So since 2012, the OpenStack community has been organized under the auspices of a US 501c6 nonprofit foundation corporation, the OpenStack Foundation as such. And in the OpenStack Foundation has both a corporate and an individual membership. There are platinum and gold members, corporate members of the OpenStack Foundation. Then there are corporate sponsors. They also make a financial contribution to the OpenStack Foundation, albeit a smaller one than the full members. And then we have, companies have the opportunity to basically declare their support for OpenStack and become supporting companies and are also listed as such on the OpenStack Foundation's website. And I checked last week, and if my count isn't off, I had 381 companies at the time that were either members or sponsors or supporting companies. And it's all across the industry, like basically you name a company, most likely they have declared some form of support for OpenStack. So that much about sort of the basics of OpenStack really, and now I want to talk about high availability. Which is part of sort of my personal history with OpenStack. I did open source high availability solutions before I got into OpenStack. And so as a result, back in 2012, spring of 2012, we had an OpenStack summit in San Francisco. It was my first OpenStack summit that I went to. And I had, to the best of my knowledge, I had the first session that was ever scheduled at an OpenStack summit that had infrastructure high availability in the title. And this being my first OpenStack summit, I basically went there and I thought, oh, well, this is going to be relatively smooth sailing. We're gonna identify sort of the shortcomings in OpenStack high availability, and everyone would agree that the platform would need some form of high availability, and then we're going to hash out sort of how we're going to best do that. And I found myself actually arguing with half of a room full of developers whether OpenStack needed any HA features at all. And it was a very puzzling development to me, but what happened was there was a group in the room that said, well, if your application can't handle the failure of any component of your cloud, then your application isn't cloud ready to begin with. Which is a different way of saying, well, we find building HA into the infrastructure too complicated, us being some of the sort of most top-notch cloud and infrastructure developers in the world. So we're just going to push this off to our users. And this, in turn, is sort of a way of saying, oh, we're not going to do it because it's hard. And then the standard reaction to that is kind of this. And thankfully, we put the whole thing sort of to an impromptu vote. I actually asked for a show of hands, so who in here actually thinks that OpenStack doesn't need any kind of HA? And then several hands went up proudly, and then I asked again, so who thinks we do need something like that? And then everyone else in the room raised their hand, and the question was settled, and then we moved on and thought about, okay, how can we best do this? And since then, a lot of things have changed for the better, thankfully. So let's see fast forward to 2016, what the current state of high availability in OpenStack is right now. So the first thing, and the important thing is when you're talking about a cloud platform, when you talk about an infrastructure as a service platform, there's multiple aspects. There is no one thing that you can make highly available. There's multiple aspects that you need to look at. And I'm going to start with one of the easy ones, which is you're going to need high availability for the service, the API services themselves. A standard feature of any cloud platform, that's true for OpenStack just as much as it is for CloudStack or AWS for that matter, or any other cloud platform, is that by convention, you have API endpoints that are RESTful web services, right? And you need to make sure that those are available. If you don't have these API endpoints, then you can't fire up a new VM, you can't define a new virtual network, you can't upload an image, you can't create a virtual router, nothing. So you have to have high availability for your API services. And that, thankfully, that's a done deal now. That's a question that has been settled and a problem that has been solved in OpenStack. Not actually in upstream OpenStack, like in the actual OpenStack code, but by agreement of pretty much everyone building any kind of solution around OpenStack, they're all doing it the same way. What's nice about the design of these API services is something that the OpenStack developers agreed on very early on, which is that API services are inherently locally stateless. So that is to say, whatever persistent data an API service needs to generate and store, that needs to go into a relational database. And it's not really allowed to keep any other state outside of that. What that means is that you can always kill one service, one instance of a service, and spin up a new one. And you can always have as many as you want, and because they're all effectively web services, you can stick them all behind HA proxy or a load balancer or whatever. And that's the HA that you get. And this is an example of a reference implementation of that. This is from the Red Hat Stack blog, but this isn't by no means specific to RHEL OSP, which is the Red Hat Enterprise Linux OpenStack platform, which is Red Hat's OpenStack-based commercial product. The way this works is you get a, this doesn't quite have the intensity, yeah, there we go. You get a highly available and replicated MySQL database. You use that with Galera. Galera is a write-set replication implementation for MySQL. That's a very dependable and very well-known and well-understood solution. So that covers the question of where do we store the data that needs to be persisted and replicated. And then you have, for each and every one of the OpenStack API services, that could be your compute service, Nova, or your image service, Glance, or your volume service, Cinder, and so on. You simply stick those behind HA proxy. You then ensure that the HA proxy virtual IP addresses are kept highly available by the Coruscant Pacemaker cluster stack, which is the default high availability stack on the Linux platform, and that's that. So this is a solved problem. We have best practices for this. This can be easily automated with any kind of automation tool for automated OpenStack deployment. That's pretty much a done deal. The next thing, you might want to provide, or you will need to provide, some form of highly available storage for your virtual machines. So your users, your customers on the cloud are going to have their virtual machines generate some data that you're going to want to persist. So you need some form of storage high availability. You have a very easy way of doing that with OpenStack, and that is just to use Ceph. Ceph, the distributed storage platform, which provides you with software-defined storage on any kind of commodity hardware. I'm not saying that Ceph is the only solution that will work for you. I'm saying that you always have the option of using Ceph. You might have workloads that demand specifically low latency. In such a case, perhaps Ceph is not the greatest option for you. You might be locked into a business relationship with a storage vendor like EMC or NetApp or whatever, and you might want to use and integrate those for including their high availability facilities with your OpenStack. You can do that. You have a bunch of backend drivers for that as well. So that tends to be a solved problem as well. A third thing is something that all those of you who have used, for example, Citrix Xen Server or who have used VMware will be quite familiar with, is the ability to simply declare a virtual machine as highly available. Basically, tick a checkbox for when you define a VM that says or that means that if the physical box that that virtual machine runs on happens to fail, that virtual machine should be recovered somewhere else. Now, this is something that wasn't and still isn't built into OpenStack upstream proper itself. However, again, we have solutions available. In this case, most of the credit goes to the engineering folks at Red Hat and SUSE, who do provide this facility, again, through clever use of the CoreSync pacemaker cluster stack. So again, not reinventing any wheel, but just making use of existing high availability technology that has been ubiquitous on the Linux platform for the better part of 10 years. And of course, you also have other means of ensuring high availability for your applications, such as the OpenStack Magnum project provides you with an automated facility to deploy Kubernetes clusters. And there's a few others as well. There's a few third-party options that you have. And there is something that comes out of the telco space, or more precisely out of the NFV, the network function virtualization space. And this is a nice tie-in to Dimitri's earlier talk. Maybe you noticed that he had a slide on the Gartner hype cycle. Did you see what was like at the very top of the peak of inflated expectations? One thing was standardized infrastructure stacks, right? And what was the other one? Root cause analysis. Like in your slide, it actually was right there at the top, root cause analysis. So we now have root cause analysis tools for OpenStack. Maybe this means that we're sort of at the peak of inflated expectations right now, and we're about to fall off a cliff. I don't know. We'll see. But I want to show you something which is I think a pretty interesting thing to look at. This came from the OpenStack Summit. It was a keynote during the OpenStack Summit where they demonstrated the resiliency of a complete well, basically a mobile phone subscriber stack that they had like in a rack on the stage. And the first part of the demo was they were doing a phone call over that stack and then just physically removed one cable, or two cables actually, and the call dropped because there is no connection there anymore. But provided that you do have a redundant setup and automated root cause analysis and automated fault detection and automated fault recovery, that means that you can now do things that are a little more involved. And so here's that demo.
All right, Ildiko, let's try this again. And I'll try to behave myself, but no promises. Let's make one more live phone call from the stage.
So now this uses Congress and Vitrage and OPNFV Doctor.
Not really you, Mark, though.
For RCA and automated failure detection and recovery.
Ildiko, is that you?
Yeah, this is me, Heather. I'm so sorry. So Mark, our chaos monkey, just unplugged.
For real this time.
But now we have
no going back, man.
turned on, so hopefully everything will go fine.
Oh, that's great. I'm sure that
So this is
will,
the simulation
help
of the
things,
ubiquitous
a lot,
backhoe cutting the cable.
Enabled in OpenStack.
I can't believe they trusted me with these.
So, are we able to mark-proof the phone call?
Yeah, the phone call is not totally mark-proof. The cables are cut.
So you can of course watch the whole demo there, which will give you additional context. And there's also a talk from the OpenStack Summit from this guy here from NEC, where they explain in more detail of what's happening here. What you're seeing there is sort of an overlap or an interesting collaboration between two OpenStack projects, Vitrage and Congress, and on the other hand, Dr. from the OPNFV project. OPNFV is the Open Platform for Network Function Virtualization. This is a Linux Foundation-driven project that builds basically a reference NFV stack for a telco NFV use case. And what you saw there, there's even in the keynote they explain a little more detail there, is when the one network link is cut, but you do have the ability to still fire up a VM in a different quote-unquote data center that is, or a different pod that is still available or addressable via a different network link, you just fire that up on demand, and so the call actually doesn't drop and you're happy. So we do have the capability now in OpenStack to build pretty advanced high availability solutions. I think we're on a pretty good track there. So much so that OpenStack is sort of gaining ground even in sort of the carrier grade telco scenario. And I think that's a pretty impressive thing to look at within like 4 years. And now let's talk a little bit about DR. On the other hand, right? Because remember, high availability is protecting services against physical failure of a relatively limited scope. Like things like a machine going down, a switch port going down, a network connection going down, and so forth. Disaster recovery is for bigger things. Your data center being flooded, or a plane crashing into your data center or something like that. And in OpenStack, we also have pretty impressive DR capabilities sort of built into the platform. One such thing is whenever you talk about preparing for disasters and doing disaster recovery, you're always talking to some degree about geographical redundancy and geographical distribution. In OpenStack, we call this a multi-region cloud. So a region in a distributed OpenStack environment is simply a self-contained OpenStack installation, effectively a full-blown private cloud, and it is linked with other OpenStack installations through only a handful of OpenStack services. This is a reference graphic from the OpenStack documentation. What you're doing is you're building these multiple clouds in multiple data centers. They all have their own compute environment, they have their image storage, they have their own controllers, and you then link them via selected services. So for example, you would synchronize the information in the OpenStack identity service in Keystone from one region to another, so that you're able to use the same user credentials here and there. There's multiple ways of doing this. You can, for example, do this by sticking your Keystone data into LDAP and then replicating the LDAP data, thereby, again, not reinventing the wheel, but simply using a protocol that already has very well established replication protocols. You can also link these individual regions on the object store side with the Swift global clusters or Ceph Rados gateway, and you typically also have sort of a unified web front end with Horizon. So again, this is a relatively done deal. This is something that has not been really hard to do for some time now, thanks to the architecture that built this multi-region concept into Keystone from the get-go. and also the ability to get asynchronous replication on the object store side, which has been around for something like 3 years. So this solves sort of the first building block. You can have your cloud distributed across multiple locations. The next thing that you're going to think about, I already mentioned previously, you want some form of storage high availability within your individual regions. And now you're also going to want some form of storage replication between regions. Now, all persistent storage in OpenStack is handled by the OpenStack block storage service, or Cinder, at least as far as directly modified data from virtual machines is concerned. And Cinder comes with built-in support for volume replication. So Cinder has in its API the ability to like flip a switch for a volume to be replicated. It doesn't, however, implement that replication itself. That is up to the Cinder backend plugin. So Cinder does not itself set up like a replication stream, but it relies on things like EMC, SRDF, or RBD mirror and Ceph and so forth to achieve that. So that's something that you do have available in the OpenStack API, and it's built into the OpenStack architecture. Whether it actually is useful for your use case depends on, again, your choice of storage technology for your persistent VM storage. Then we have something else that comes in very handy when you want to build distributed multi-site clouds, is the ability to do full-blown automation of your application deployment. And here you've got options galore. You've got a service that is built into OpenStack directly. That's OpenStack Heat, the OpenStack orchestration service. This allows you, if you're familiar with AWS, that's OpenStack's flavor of AWS CloudFormation. And it allows you to define arbitrarily complex environments, something like whatever. Let's say you want 50 servers in 3 different networks with 2 different network zones and 3 different security groups with such and such load balancers in front of them and so forth. It can be arbitrarily complex. You put all of that in one template definition. You can equip that with parameters and what have you, and you can simply fire that at a cloud and it will spin that up for you. So that is something, if you can deploy all your applications that way, it basically means that you can deploy to any region in your cloud wherever you would like. That is only the OpenStack built-in facility that you have for this. If that's not for you for any reason at all, you have a bunch of other options as well. You can use the Juju service orchestration facility from Canonical. You can use Ansible. You can use Cloudify, which also enables you to define your cloud environments using an industry standard, in that case Tosca. You can use Cloud Foundry. You have a bunch of other options. So this also being built into OpenStack pretty much from the get-go and having the ability to deploy OpenStack to whichever region of your cloud you like is a big advantage here when it comes to planning for disaster recovery. And when you think that through to the end, then obviously you're not going to just be interested in running or being able to run a workload in region A or region B or region C of the private cloud or private clouds really that you control. You're also going to be thinking about, well, can't I run part of my service in my private cloud, and can I not run some of my services in a public cloud, either from the get-go or on demand? And this is something that we call either hybrid cloud or cloud bursting, where you might want to be able to deploy an OpenStack virtualized environment both on your private cloud and on a public cloud. And this is where OpenStack interoperability comes in really, really handy. You can, with some limitations, actually expect to run an unmodified, say for example, Heat template, an OpenStack orchestration template, or for that matter, an Ansible playbook that runs against an OpenStack cloud in just about any OpenStack public cloud out there. And that, again, was something that was demonstrated at the OpenStack Summit. At the OpenStack Summit, we had this interop challenge where there were 16 different cloud providers that were all tasked with running the same playbook. I'm not sure, but I think that's sort of the largest such demonstration of any cloud platform that was ever attempted. And it worked really nicely. So that's another good thing that you've got going for you. And quite frankly, as a cloud consumer, it also improves your bargaining power with your public cloud provider because you know that you're not locked into them either. If you want to deploy a specific service and it doesn't work with a specific cloud provider, then you can tell them, hey, make this work because it works somewhere else. And you know that you're not locked into them, which is helpful and then facilitates competition. So in summary, for OpenStack, high availability and disaster recovery, infrastructure, API, high availability, done deal. Easy. We've got best practices for this. They're automated. They're easily deployable. You can just use this. Application HA, you've got that too. You actually do have multiple options as far as that is concerned. You do have Magnum. You do have the ability to define even high availability policies in heat and so on. You have multiple options for doing storage high availability. The Ceph preferred part tends to be like my personal opinion. You may disagree, that's fine. But you do certainly have multiple options for highly available storage, persistent storage for your VMs. Virtual machines, you get that too, albeit currently in a vendor-specific fashion. Upstream streamlining there is underway. So just at the OpenStack Summit, there were a couple of sessions with developers from SUSE and Red Hat and a few others, where they're getting together and unifying that effort and upstreaming that. Multi-region cloud, easy, you can do that. Again, with some limitations. For example, one of the things that is currently still a bit tricky to do is building a multi-region cloud with a single multi-region virtual Ethernet broadcast domain. So basically a single flat Ethernet network, virtual Ethernet network that goes across multiple regions. There's some vendor-specific options that exist for this, but at least upstream, that's currently something that's still pending. Anything that needs sort of layer 3 connectivity, or if you're fine with VPN as a service between two clouds, that's done. You can do that as well. Replicated storage, you get that too. You get that from for volume mirroring, you get that for OpenStack Swift with Swift Global Clusters. So that's available as well. Multi-cloud deployment, you can do that. You can do that with a variety of tools, Heat, Ansible, Juju, and others. And you do have a reasonable expectation of a cloud, a specific OpenStack workload to be supported by one cloud, whether that's private or public, just as well as it is by another, which can also be private or public. I know we're running a little behind on the schedule, and I'm not German, and I've heard that not stopping on time is a deportable offense here. So before we get to questions, I do want to share this. These slides are available under a Creative Commons attribution share-alike license, so if you would like to use them or reuse them, you can by all means do so, and here's your QR code for the rendered slides again. And with that, I'll be happy to open it up for questions. Yes, sir. I'm sorry? Go ahead. Thank you. Yes.
So in that context, the question comes around, you showed a very nice application of the Google Spring Cloud, where the only requirement for that to work is not to have enough latency for additional not to be very.
You may have specific or application-specific requirements that may. What is that? I'm being deported? Yeah. Okay. I'm over time. Oh my God, they're coming. Sure. So consistency issues are always application specific, and there are multiple application specific ways that even OpenStack APIs deal with. So for example, one of the things, actually something that has been subject to debate or discussion for some time in the OpenStack community, is that OpenStack has, with the adoption of its big tent development approach, has sort of moved away from just being an infrastructure as a service and compute platform to something that also provides a bunch of services around that. And so if we talk about database consistency, there is actually in OpenStack a database as a service project called Trove. And with Trove, you can do things like deploy a MySQL, or for that matter, even a MongoDB cluster. It doesn't limit itself to relational databases, but also talks about distributed or non-relational key value stores. You can effectively do that with like one API call. You can do a Trove create cluster and then lean back and you get your MySQL cluster, your MongoDB cluster, etc. So what OpenStack aims to do for you is basically just the right thing for that specific application. With that said, yes, you will always run into some application specific consistency questions that you're going to need to solve either in your application or within the respective OpenStack API service. But we can happily discuss that after the next talk outside.
Just ask two small questions from my side. So I understand your explanation for the multi-cloud scenario. When you have multi-clouds, how do you handle consistency there?
You mean okay. So if we're talking about a multi-region support, is just so I get the question correct. Are you talking about so what happens to my database, for example, or the content of my database as say an A380 drops onto my data center here, then that's being replicated over there? What? Yeah. Of course, yeah. I mean, it's a general given, pretty much, that once you talk multi-region support, you're talking primarily about asynchronous replication, whatever it is that you're talking about, whether that is block storage or whether that is a database replication or whatever. And so, to be quite precise here, the only thing that this can guarantee for you is consistency, as in not having broken data on the other end. What by definition asynchronous replication cannot guarantee for you is having data on the other side that is exactly the same as you had originally, because if you wanted that, then you'd have to build synchronous replication, which are sort of very standard trade-offs. The general assumption is usually if one of my data centers burns down, it is better to have data that is a little outdated rather than no data at all. However, that doesn't absolve you from resolving the questions that you need to resolve for your application for that time warp, right? And it's very, very dependent on what it is that you are replicating, whether any such jump back in time is acceptable. If it's just a click-through data for your website, probably you couldn't care less. If it is financial transactions in the PCI DSS compliant database, you're probably going to have a problem if you just throw like 3 or 4 away. There you go.
So one question to you
Wait,
and a question.
wait. Do we have a question over here?
I'm just going to finish it
Okay.
off that applies to you and all the other clouds. So far, I've been hearing about reliability, no from a fault or a crash viewpoint. How do the same techniques or how do the opinions change when you deal with attacks rather than just with faults from a security perspective?
So I'm not going to go down the security rabbit hole here. There is, however, a very interesting talk that I can recommend on that subject. It is by Major Hayden, who is he was at one point the chief security architect at Rackspace, and he is now a principal architect for private, I forget his actual current title. but he has a very interesting talk from the OpenStack Summit in Barcelona. It's called Holistic Security for OpenStack Clouds. It's up on YouTube, and I highly recommend that you watch that. He also put up a blog, a write-up on his blog, and that's majorhayden.io. So please do check that out, because he's a far more knowledgeable expert on that than I am.
So, talking about, you pretty much said that API HA is pretty much done, but on the control plane, you also have those infrastructure services, right? Like the Galera thing, the RabbitMQ.
Yeah.
So
those really are the two important ones.
And what will you think are the next steps in HA for OpenStack on the control plane? And if you can go a little bit deeper on the VM that Red Hat and SUSE are doing.
Okay.
How could I connect there?
All right. So there were several things in that question. One, yes, you're right. There are basically two core infrastructure services that are not part of the OpenStack code base proper, but that are heavily used by OpenStack. Those are RabbitMQ and MySQL. For both of those, again, we have very well established best practices on how we achieve high availability for those, and pretty much all the vendors do it the same way. It doesn't really matter whether you're deploying your OpenStack cloud with Mirantis Fuel or with RHEL OSP Director or with Crowbar for SUSE Cloud or with Juju or OpenStack Ansible on Ubuntu. They all pretty much use the same approach there. So that's pretty much a done deal. The second part of your question was, remind me?
Like the next steps for HA on control plane for OpenStack.
Right, and then you had one other thing.
For the data plane thing, the VM availability.
The VMHA, yes, thank you. So about the next steps, my crystal ball just fell off the podium here and broke. So I'm not. I can't really comment on sort of like what I'm expecting there next in the control plane. There are certain interesting things, specifically on the Neutron side, and a few others. What I will go into a little more detail on is the virtual machine HA part, which is there again. This basically ties into what you already have in the Linux, in the pacemaker-based Linux high availability stack. The weakness of that stack historically was always that based on the CoreSync totem implementation, which didn't really scale very well beyond 16 nodes. Because of that, you could simply not build clusters significantly larger than that, and that changed a little while back with the introduction of Pacemaker Remote. In a nutshell, that means that you can run a core pacemaker cluster that's overlaid over a CoreSync cluster, and then you have more or less satellite nodes that only run the pacemaker remote daemon. But they can and they can pretty much do everything that any other pacemaker node can do, except contribute to quorum and initiate fencing. So they can be fenced, but they can't contribute to the fencing decision because you want that virtual or pseudo-virtual synchrony layer on the CoreSync side there. And so the idea there is that your Nova Compute nodes become pacemaker remote nodes, and they manage the virtual machines as pacemaker remote cluster resources. It's basically the approach there.
Florian, thank you.
My pleasure. Thank you.